Hi everyone, my name's Kev. I'm a PhD student at the University of Leeds, and this year I was invited to give a talk at the Lyme Regis Fossil Festival. However, given the current situation around the world, I was invited to record a talk for the virtual Lyme Regis Fossil Festival, so that is what I'm doing right now. But before we get started, I thought I'd just throw in a few facts about me, given that I can't see you and you can't see me. So as I mentioned before, I'm a current PhD student at the University of Leeds. I was originally from Merseyside. You can just about pick up a slight hint of Scouse in my voice. And between 2014 and 2018, I did my undergraduate at the University of Cambridge, studying natural sciences and specialising in earth sciences. I'm now doing my PhD research on volcanology. So what is volcanology? Well, volcanology is the study of volcanoes, the processes generating the magma which forms them, how they erupt, and ultimately the effect they can have on human lives. And a general rule of thumb in the geological world is that volcanoes are found near plate boundaries, as these are where tectonic plates are made and destroyed. Most volcanoes found above sea level at the present day are found where plates are destroyed. For example, the western coast of America, which includes the volcano Mount St. Helens, which dramatically erupted in 1980, and also in the Mediterranean, for example, Mount Vesuvius, which is best known for destroying the Roman settlement of Pompeii in AD 79. I, on the other hand, look at volcanoes where new crust is made. I study continental rifting and the volcanoes that form during the rifting process. Continental rifting is the breakup of a continent to form new oceans, and it's marked out on this animation by those red lines. It's one of the key elements of plate tectonics, and it counterbalances the material that's returned to the mantle by subduction of old oceanic plate. It also shapes the continental layout of Earth, and is an important source of volcanic carbon, the form of carbon that's released during volcanic eruptions. Rifting was more extensive in the past, as you saw just then during the breakup of Pangaea, but at the present day, the only significant rift system is found in East Africa. The 6,000 kilometre long East African rift system is the largest present-day continental rift. Along this rift, East Africa, termed the Somalian Plate, is being torn away from the rest of Africa, termed the Nubian Plate. Rifting rates from GPS stations, as shown by the figure on the left, range from a centimetre per year in Mozambique and southeastern Africa to 5 centimetres per year in Ethiopia and the Afar Depression. As you can imagine, if you break the Earth open, it produces quite a lot of damage. A lot of earthquakes are therefore observed over short periods of time. An example of this is the figure on the right from a series of stations in northern Ethiopia that record about 2,000 earthquakes over the space of a single year. With these earthquakes come lots of volcanoes. And it's worth mentioning at this point that there seem to be a lot more in the north of the rift than in the south. These volcanoes are taken from the Global Volcanism Programme and are those red triangles that you can see on the globe in front of you. A problem that modern geophysics scientists have to deal with is that we don't really know how we go from continental rift zone to spreading oceanic centres. Rifts show immense variability in their style over the course of a single rifting event. And we only really know what's happening by looking at what's going on at the surface, and also by looking at geophysical features, by studying earthquakes and the seismic signals they produce. We know that at the earliest stages of continental rifting, things might look a lot like this. We've got a thick crust and a thick lid to the mantle, called the lithospheric mantle. We have large faults that break the continental crust open, and along these faults we have volcanoes, because magma generated deep within the Earth can use faults to permeate their way through to the surface, where they can then erupt as volcanoes. An example of this would be the Kenyan Rift, or the southernmost parts of the East African Rift Valley. We know how it'll end up. It'll end up a lot like this, a mid-ocean ridge, with all the deformation and volcanism and earthquakes focused in the centre of the region which is being pulled apart. Here, the melting mantle is right underneath the crust, as opposed to a thick mantle lithospheric lid. So this is what's currently happening in the Red Sea and the Gulf of Aden, immediately to the north of the East African Rift. In between these two stages, we have this sort of awkward substage, As rifting develops, the lithospheric mantle gets thinner. However, crustal thickness is maintained by the continual intrusion of magma into the crust. As more and more magma intrudes into the crust, the lithosphere becomes hot and therefore becomes a lot more malleable and ductile. Border faults along the side, which were very prominent during the earlier stages of rifting, are now inactive, and volcanism begins to migrate into the centre of the rift, like as in a mid-ocean ridge. In the centre of the rift, the intrusion of magma accommodates a significant proportion of strain. It's therefore important to know exactly what the mantle is made of and how much magma is being produced and how quickly it's being transported throughout the lithosphere and the crust. And this is why we have different styles of volcanism and faulting throughout the rift. In the south, as I mentioned before, we have this rift initiation stage where there's a lot of breaking open of faults and volcanoes occurring along these border faults. Whereas the further north we go, the more the volcanoes move to the centre of the rift and the less faulting plays in this extensional process. And finally, this develops to the point where we have something quite similar to that of a mid-ocean ridge right in the northern part of the East African Rift system. The subject area of my research is Ethiopia, where I'm going to try and understand exactly how magma is generated and being moved through the crust in the Ethiopian Rift. It's also worth mentioning that a significant proportion of the country lives within 100 kilometres of a volcano, and that while geoscientists such as myself are busy solving fundamental scientific problems, people are still living within this very seismically and volcanically active portion of the world and near major rift volcanoes. And while my research won't directly contribute to this, the more we understand about rift processes and how rift volcanoes operate, the better prepared we will be for preparing the people who live within the rift for major hazards that might arise as a result of them living in such a seismically and volcanically active region of the world. The best way for geoscientists to determine what's going on in a region is for us to go there ourselves and see what's going on. So in January of 2019, I prepared for field work out there. And thankfully, we were assisted by the University of Addis Ababa. Our field assistant was Yared from Addis, who was a master's student at the time. Upon arriving at the rift, what we were aiming to do was to collect samples from different parts of the Ethiopian rift. Rifting processes have left this sort of big topographic scar running through the centre of the country, separating the Ethiopian and Somalian plateaus to the west and to the east, respectively. We chose these three principal regions, Abaya Lake, Ziway Lake, and Adama, to capture any sort of along rift differences in magma generation, magma transport, and volcanic activity. Just keep in mind, as we saw before, the southern parts of the East African Rift are less tectonically mature than the northern parts. Once we're down in the rift, the signs of rifting are very clear and obvious to see. Here we have a very large extensional fault, which is several kilometres long, and along which has about 100 metres worth of vertical displacement. You can also see that there are some small volcanoes turned scoria cones, which have formed right by that big fault. These large faults are pretty impressive from the ground. Here we have a fault of about 50 metres displacement, and it was about a kilometre in length. You can also see that there are these layers within the fault. These layers are different lava flows which have erupted from the fault and have come down from the upthrown side onto the downthrown side. The rift landscape is marked by tectonic processes. In the distance of this image, you can see Corbeti volcano, one of the major rift volcanoes lying within the centre of the Rift Valley itself. In addition, as a result of the large faults forming these extensional grabens in the rift, subsidence has resulted in the formation of these rift lakes, such as Awassa Lake, along which you can find quite a variety of different kinds of birds and hippopotamuses and crocodiles and other sorts of animals. Noticeably, near the large volcanoes, such as Corbeti in the previous slide, or Aluto in this one, are scoria cones, which form these pockmarked things which are quite noticeable to the eastern bank of ZY Lake. These scoria cones are linked to magmatic intrusions or fault systems that trend along strike to the rift. These intrusions bypass the magmatic mixing and fractionation in the larger volcanoes, and hence are a straight tap into sub-rift mantle magmas. On the larger volcanoes, sub-rift mantle magmas often end up sitting in magma reservoirs for a while, resulting in them changing their magma chemistry as a result of forming crystals, hence clouding over any sort of signal that might be preserved from the time they were made in the mantle. Scoria cones are also very noticeable from the ground. This photo is taken from a side of the Hobitia caldera near Abaya Lake. And the scoria cones are these very noticeable conical hills that you can see straight in the centre of the image. Here are some more scoria cones, this time taken from ZY Lake. These scoria cones are linked with the fault and magmatic intrusion system to the east side of the lake that I showed you in the previous geological map. As you can imagine, these particular areas of Ethiopia are quite rural and quite difficult to access, so oftentimes we had to thoroughly abuse the SUV that we had with us, and our field driver had a very, very fun time manoeuvring his way up and down some of these caldera walls. Once we manage to get close to them, the cone's materials themselves are difficult to access. As you can see, it's covered in soil and this sort of very dry, grassy cover, which makes accessing the rock that it's made of very difficult. However, the scoria that comprises these cones are often used as a road building material in Ethiopia, so quarries such as this one often provide really good access into the cone itself. In some cases, the stratigraphy within the cone is also very noticeable, so you can sort of track the eruption of this one particular cone along its lifetime, if you want to, by collecting different samples from different parts of the cone itself. And near the major city of Adama within the rift, these quarries are quite significant. Right at the bottom of this photo is a small pickup truck and some men for scale. Once we got access to a cone, for example via a quarry or via a road cut into the side of the cone, we then began our sampling. And this was mainly done by shoveling the material of the cone itself onto a soil sieve that we picked up from a garden centre. That way we could then separate whatever crystals and small glassy pieces that were in the scoria from the rest of the scoria itself, making picking out small crystals a lot easier once we got back to the lab. We also sampled rocks in the more traditional way by thoroughly applying a hammer to them. Here Yared is sampling some rock on the side of a fault along which a lava flow is going down from the right hand side to the left. And in some cases, streams have cut away a portion of the surroundings for the cone itself to be sampled. Here in Lake ZY you can see multiple stages of eruption marked out by those black bands, and then times when there hasn't been much eruption marked out by the lighter bands of lacustrine sediment. Here is a closer image of such a stream cut, and again you can see the scoria, which is the black material, interbedded with this lighter material, which are lake sediments. For the first part of our fieldwork, we were lucky enough to be joined by two Icelandic geochemists, Snorri Gufbrandsson and Dario de Rienzo. Snorri is a geochemist for Reykjavik Geothermal, and his company were scouting out different locations in the rift for potential for building a geothermal station to provide power to people living in the rift. Here, these two fellows are currently sampling waters from a scoria cone near Abaya Lake in order to look at its chemistry and its temperatures. There is a lot of very clear hydrothermal activity and degassing from the rift itself. If you turn the volume up, you might be able to catch the sound of water boiling straight from the side of the scoria cone. If not, then you can clearly see the steam that's emanating from the side of this hill. The instrument Snorri is using at the moment is a thermometer which he is sticking into the side of the hill, and he is recording a temperature of pretty much boiling, 100 degrees Celsius.
Okay.
Around the corner from that hill is a hot spring site. Hot springs are an expression of geothermal activity in the rift. Water is heated at depth by the presence of magnetic bodies, hence resulting in features such as this throughout the rift.
Hot? Very hot.
Features such as this are the reason why companies such as Reykjavik Geothermal are interested in establishing geothermal sites in the rift. And finally, I just want to make a quick note on the villagers who lived in and around the Rift Valley, who we interacted with on a daily basis when we were going about our fieldwork. As you'd expect, they don't really see too many people like my supervisor or myself in and around the rift, and so they were all very curious and intrigued as to what we were doing, and we did take some time to explain to them that we were scientists and looking at some of the hills and faults that occurred around the rift here. And of course, whenever we drove off, a whole load of them would chase after us, asking us for our water bottles, which they would take with them to fill up at wells and local springs. However, though, soon our field trip was over and we were able to return back to the University of Leeds with about 80 kilograms worth of Ethiopian materials, most of which are basaltic scorias collected from those scoria cones, but also some ashes, some obsidians, and various other geological entities that, you know, every now and then you'll just walk along a road and see something like, oh, I'm going to pick that up and put it in the bag. And so that's what we did. So what now? Well, what I'm doing is I'm using the chemistry of these different rocks and minerals to say a bit more about how magmas are transported through the rift, up the rift, and how they're made under the rift itself. An example of this is the figure on the left here. If we look at the total sodium and potassium content and compare it to the silicon content of these different basaltic materials, we can say what kind of rock they are. In this case, quite a lot of the materials lie within 45 to 52% silicon and within 0 to 5% sodium and potassium. We can therefore say that most of these rocks are basalts, which is what we identified them to be as in the field. A more complex part of my project will involve looking at these. So on the left-hand side, we have an olivine crystal. Olivine is the first major crystalline phase to form from a mantle-generated magma. And it is this greenish mineral that you can often find in black basaltic rocks. Within them are these small little blobs with little circles in them. These brown blobs are inclusions of magma, so as the crystal was growing, it can trap small blobs of magma within itself. Because magma contracts when it cools, it gets smaller in volume. The gases and various volatile parts within those little blobs can then escape to form a little cavity called a shrinkage bubble. And so those little circles that you can just about make out in those brown blobs are little bubbles of gas trapped within the magma, which itself is trapped within a larger crystal. And here's a zoomed in picture of it. Now, what I was intending to do before the shutdown was to analyse the contents of the gas bubble and the contents of that little magma blob in order to determine the amount of carbon dioxide carried by these magmas. By doing so, we'd be able to say a lot more about the carbon dioxide that rifts can contribute over the course of millions of years to Earth's carbon cycle. However, as a result of the shutdown, I've been unable to progress with this kind of stuff. So fingers crossed I'll be able to continue with this line of research in the near future. I'm cautiously optimistic. So that's all I have to present to you today. If you have any questions or queries at all, feel free to get in contact with me on Twitter or to email me using my University of Leeds email account, which I've shown there. Thank you very much for listening, and hopefully I'll be able to speak again at this event face to face in the near future. Thank you all once again.